Do language models need sensory grounding for meaning and understanding? And we have 3 yeses and 3 nos. The yeses are Yann LeCun, Brendan Lake, Jacob Browning, all 3 from NYU. The no's are Ellie Pavlik from Brown, David Chalmers from NYU, and Gary Lupian from Wisconsin. The order will be, we'll have a yes and a no and a yes and a no, et cetera. Yann is going to go first, then Ellie, then Brendan, then David, then Jacob, and then Gary. And I just want to say 1 or 2 words about what the topic is. So there really are 2 issues. I've looked at people's slides, and there are 2 issues. One is an issue of reasoning, whether you need sensory and motor connections to do certain kinds of reasoning behavior. It's a kind of behavioral thing. The other is whether there is a kind of abstract content that doesn't require those sensory and motor primitives. Okay, so Yann, you are first. And I'll get Yann's slides up. All right, show. There you go.
Okay. All right, this is not actually the first slide. All right.
Okay.
All right. Do language models need sensory grounding for meaning and understanding? The answer is yes.
I can't hear you, right?
You can't hear me. Now you can hear me, hopefully. So the answer is yes, hopefully. I mean, certainly. So first, current AI systems or machine learning-based AI systems really suck compared to human and animals in terms of their ability to learn. So we all know the limitations of supervised learning. It requires maybe many labeled samples. Reinforcement learning requires insane amounts of trials. And obviously we're missing something big because we still don't have domestic robots and self-driving cars. And so how is it that animals and humans can learn so fast? So in recent years, self-supervised learning has been sort of taken over the world. And they do require a large number of unlabeled samples, but unlabeled samples are cheap, so that's a big advantage. But the problem is current systems really make really stupid mistakes, and they can't reason, they can't plan, and they don't really have kind of an understanding of the world, and that includes large language models. I'll come to this in a minute. In comparison, animals and humans can learn new tasks extremely quickly, relying on their background knowledge about how the world works. They do understand how the world works. They have pretty sophisticated world models. They can reason, they can plan, and they have common sense. That's perhaps the accumulation of knowledge that allows them to have common sense. So current machines, not so much, or a little bit, but it's very superficial, and we need to make them non-superficial. So self-supervised learning, SSL, has really taken over the world. And it's the idea that you train a system to predict missing information, temporarily missing information. So you show a piece of a video clip, and you ask the system to predict what's going to happen next in the video clip or some other parts of the video clip, and then you reveal what happens, and you expect the system to be able to, by training itself to predict, to have some understanding of the underlying reality. And this doesn't work. Like, we don't know how to do this today, or not very well, at least. We can do it with text. It works really, really, really well with text, but not yet with video or any kind of other sensory information. So if the answer to the question of the debate is yes, but not yet, we don't know how to do it yet with AI systems. So SSL has been extremely successful over the last 7 or 8 years or so, where the idea of filling in the blanks is you take a piece of text, you corrupt it in some way, by removing words or substituting them. And then you train some giant neural net to predict the words that are missing. And in the process of doing so, the system learns appropriate representations of language that incorporate semantics and grammars and syntax and all kinds of stuff. And it's multilingual, and it works wonderfully. And it's used absolutely everywhere. It's deployed commercially. You may not see it, but it's what does content moderation on all social networks today. and translation as well. Now, within this, there's a special case of this where what you ask the system to predict is not random words in the text, but just the last word. So you have a gigantic neural net with tens of millions, hundreds of millions of parameters, and you strictly train it to predict the last word in a window of text that typically has a few thousand words, something like 2,000 words. And when you have trained the system, you have it generate one word or a token, which may be a subword, and then inject that subword into its viewing window, and then generate the next word, and then inject that into the viewing window, generate the next word. This is called autoregressive generative models. And in the case of text, it's autoregressive large language models, if they're large. So I'm going to argue for the fact that those things also suck. They're amazing in many ways, okay? But they are nowhere near what's required for human level intelligence. So those systems output one token after another. The encoders and predictors are transformer architectures, which I'm not going to go into the details of. They typically have billions to hundreds of billions of parameters going towards trillions. They're trained typically on hundreds of billions or trillions of tokens gathered from all the text ever written by anyone available online. And that creates a problem because we don't know what the training set is. We don't have a test set because those things have been trained on the entire text of the world. So if you ask them a question, you don't know if it's seen it or not, because if it's ever been specified, the system has been trained on it. And the modern systems, as soon as you ask them a question, they get fine-tuned with the answer. So you can't ask the same question twice, or you won't get the same result. So there's been a bunch of those models over the years, and an interesting phenomenon appears, which is that as you make them bigger and you train them on more data, there is sort of emergent properties. They seem to be kind of understanding more and more about the world when you make them bigger and train them on more data. The latest one being GPT-4, which nobody knows how it's built, but ChatGPT is an autoregressive LLM. And then Llama from FAIR, that was essentially open source recently, is that. Alpaca is kind of an improvement on Llama by Stanford University. So they're kind of amazing, but they make really, really stupid mistakes sometimes, completely non-factual statements, inconsistent answers, particularly if the answer is long, logical errors. They have very limited reasoning abilities. There is no way to control them for things like toxicity or things like that. It's very, very difficult. And it's because they don't have any knowledge of the underlying reality. So they're trained purely from text, and they really don't have any knowledge of the underlying reality that all of us share and assume is part of intelligence. Those things don't have it. So you ask them questions that can only be answered by some sort of physical understanding of reality, and they can't answer it unless a very similar situation has been specified in their training set, and they remember it. And they have like a major flaw, which is that because they are autoregressive, they produce one token after another. Let's imagine we have the set of all possible sequences of tokens, and within this set, there is a small set, which is the set of correct answers, if you want. And imagine there is a certain probability E for the system to make a mistake, produce a token that takes you outside the set of correct answers. And that's the average probability for making an error. So the probability that the system will produce an answer of size n that is correct is 1 minus e to the power n. And that's an exponentially divergent process. So those systems, as soon as they start producing too many tokens, will start spewing nonsense because they are autoregressive. They don't reason, right? They don't plan their answer. They just produce one token after another reactively. And it's not fixable, in my opinion. It's not a popular opinion among my colleagues, but I don't think it's fixable. So I have a prediction, which is 5 years from now, nobody in their right mind would be using any autoregressive LLM. Okay? It's a temporary thing that we have to deal with, but they'll disappear. So they really suck. I mean, they're wonderful, they are helpful, they help us, start writing text and everything, but they're nowhere near human intelligence, and they are not a good path towards that, although they have some of the characteristics. They are an off-ramp on the highway towards human-level AI. So we need systems that can understand how the world works, and that's where grounding comes in. Babies learn how the world works. There is no language involved in the first few months of life, and they learn incredibly complicated concepts about the nature of the world, things like intuitive physics and gravity and stability and the difference between animate and inanimate objects. This is a chart I stole from Emmanuel Dupuy, who is a cognitive psychologist in Paris. And this is the accumulation of knowledge that we acquire in the first few months of life that allows us, by the time we are teenagers, to learn to drive a car in 20 hours of training. And obviously, AI systems don't do this today. We still don't have self-driving cars, so we're missing something big. So I think that sort of gives us the challenges for AI and machine learning for the next few years. Learning representations and predictive models of the world. I'll come back to that concept, using self-supervised learning mostly. Having machines that can learn to reason. So basically, autoregressive LLM and most machine learning systems today are like Kahneman's system 1. They're reactive. We need AI systems that can do system 2. Basically, they can plan their answer and kind of reason before producing an answer. And systems that can learn to plan complex actions. Okay, so to approach that problem, I've written a position paper, fairly long, but fairly readable, hopefully. And it's on open review, so you can comment on it. That's the URL. It's been around for several months now, since June last year. And it's based on a cognitive architecture that's built around this idea of world models. So the system has a world model, or would have, that predicts what's going to happen in the world as a consequence of its actions, and basically has a reasoning mode where it imagines a sequence of states that the world may go through as a consequence of a sequence of actions that is imagined. And then you optimize the sequence of actions so as to minimize a particular objective, a cost function of some kind, right? So the general model for this is very old. It's called model predictive control in optimal control. But we'd like to do this with complex models of the world that are learned, and then perhaps complex inference procedure that figure out sequences of actions. And we also would want to do this in ways that are hierarchical. I want to skip to that here. Okay, so that so things like this, where we don't make predictions at one level of abstraction, but we make predictions at multiple levels of abstractions, which allows us to do long-term planning in sort of abstract representations of the state of the world. And that's kind of a general plan. Nobody has really built this. Nobody knows how to make this work yet. But this is basically where I think AI research is going for the next decade or so. I'm advocating also for an architecture. So there's one slide I want to show that I skipped. This one. It's a bunch of recommendations that are very unpopular in the machine learning and AI community, which is that to handle the uncertainty in the prediction, we have to abandon the idea of generative models. So all the stuff that people are excited about today, they work for text, they don't work for video. And if we want to have world models that work for video, we have to abandon the idea that we're going to predict every details in the video. So we have to use architectures that are called JEPA, Joint Embedding Predictive Architecture, which is drawn on the right here. So no generative model, no probabilistic modeling for reasons I'm not going to explain, and no reinforcement learning, or at least minimize it. So that's it. Let me just show one set of position and conjectures. Prediction is the essence of intelligence. We knew this, we've known this for a long time. Almost everything is learned through self-supervised learning, and almost nothing learned through reinforcement or supervision or imitation or anything like that. Reasoning amounts to optimization with respect to a sequence of action, optimizing an objective. I'm recommending this hierarchical JEPA architecture, but that's a technical detail. Those systems will need to have intrinsic costs and costs and objectives that determine the function they're supposed to fulfill. And that will make those systems controllable, which is not the case for current large language models that are not controllable. And those cost functions will sort of provide the equivalent of emotions, if you want, for AI systems, because they're basically anticipation of outcomes. Thank you very much.
Joe.
That's the last slide.
That's the last slide, sorry.
I don't want to.
Our next speaker is Ellie Pavlik. On the no side.
All right, thank you. All right, so the main kind of argument I want to make is that this is mostly going to be an empirical debate. Is the mic okay? And if we just look at kind of the current empirical data we have on the models we currently have, kind of focusing precisely on this question, I think the answer is obviously no. So there's a lot of in principle arguments that we can make about why we don't need grounding necessarily a priori for meaning. These take a couple forms. So there's this roughly internalist kind of an argument you can make. This would be saying that what it means to have meaning is to have the kind of the right associations between concepts and words inside the head. And we don't really have any good reasons to think language models can't learn the same types of associations that humans have. A lot of people don't like this kind of argument because it seems, weird or unsatisfying to say that you can have meaning kind of just in the head, completely untethered to reality or reference in the world. But I think even along that line, it's hard to make a case that language models can't kind of inherit that grounded meaning in the same way that we humans inherit a lot of the grounded meaning we have, which is to say we learn from other people who have that grounded meaning. So there's a good example in Harman and elsewhere about the meaning of like oak tree and elm tree. Like I can use those words, I use them very freely, and I can say hopefully meaningful sentences, including them, but I honestly have no idea what the difference is, and I could not tell you the difference or identify the difference in the real world. So I'm mostly going to leave it to Gary and David to talk more about these various more in principle arguments. But I want to focus on basically we're having this debate because there are specific models, these text only large language models that really seem to have a lot of meaning in them. And that's kind of why the debate is relevant. So we don't have to have this debate kind of in the abstract. We can be thinking about specific models. And I should say that kind of responding to Yen, I think it doesn't have to be the case that these models are perfect yet. Imperfect models doesn't mean that like some future model that looks very similar to these might have meaning. So we want to focus on the specific questions we're trying to ask and show kind of what does the empirical data show right now. So models making mistakes, I don't think is an argument that says that grounding is necessarily necessary for meaning. So I want to focus on two kind of conclusions that I think are supported by current empirical data. The first is that if we add sensory grounding to these models, we don't see improvements on things. So it's true that they're not perfect at stuff. They make a ton of mistakes. But right now, adding in the sensory grounding doesn't make a difference. So this could just be neural net problems or something with the architecture, something with the algorithm. It could be some other thing, but it doesn't seem to be that sensory grounding is the difference there. And then I think there's a richer argument to make about when we actually look at the representations that we have within the language models, that they're actually quite similar to what we would expect representations of the actual world. And so much so that we can actually ground the language models post hoc with very little effort in doing that. So for this first point, I want to say, like I said, it's really hard to show a difference between text-only representations, text-only models, and models that have sensory grounding when we compare them head to head. And this is actually coming out of a study where we were trying to show that there's a benefit to having some sensory data, because I have a lot of colleagues and students, and we work on this, and we wanted grounding to make a difference, right? And we were annoyed that a lot of the studies that were out there didn't seem fair to the grounded models because the text models have larger data and they have richer data. And so we've said, and have different architectures and things. So in this case, we're using one of these kind of masked language modeling type of models. This is a model called VideoBERT. It's very similar to BERT. We're kind of predicting the missing tokens, and those tokens might be words or they might be video tokens, right? And then we're going to train an identical model. We're just ablating the visual part. So here, the language is the same, the amount of data is the same, the architecture is the same. And so we're just trying to see if there's any effect at all from having this additional sensory information. And the short answer is no. We tried very hard, but the models perform extremely similarly. We looked at a physical common sense reasoning task called PICA that was designed to kind of make the case that large language models need access to sensory grounding, but then when you add sensory grounding, they don't do better. We looked at some various semantic probes, so this would be kind of meaning in a linguistic sense, things like semantic roles and co-reference. Models perform very similarly there. We looked at some adjective noun relations. So this would be like when you have a word like apple, does the model kind of know the state of the apple, whether it's chopped up versus whole? And again, we see models perform very similarly there. So across the board, with the models we have and the metrics we have, adding sensory data doesn't help even on these kind of metrics of understanding where we really would have expected it to. So as I said, I think you can go further. So that's kind of based on their behavior alone. There's not strong evidence that sensory grounding is going to make a difference. But then you can also look at actually the structure of the representations that the models learn. And I think there you get an even stronger case to say that what these models are learning really does look a lot like what we would consider to be meaning that you would get through sensory grounding. So we can look at a domain like color, which is arguably kind of a really clear case where we would expect sensory grounding to matter. And what we might say is that language model has some kind of geometry of the concepts up in language space, and that it knows some kinds of relations between them. So it knows there's some direction that is associated with the word dark that takes blue to dark blue and green to dark green. But this is just all up in language text land, right? But of course, if ideally this corresponds to some structure in the real world that you would get through perception. And so if the model is doing it correctly, we should be able to show it some examples of the kind of grounded concepts. So we could say this is blue, this is dark blue, this is green. And from that, it can learn that this is kind of how the dark direction in text space is realized in the perceptual space. And it should be able to infer what is dark green once you ask it to label that color. So we looked at this we were looking at GPT-3 in this case. And in the color case, we look at a few domains: direction, spatial orientation. Color is the one I'll focus on. And we're basically just asking it to label RGB codes, right? Now, of course, the model's probably seen many tables of RGB codes, so succeeding on this is not particularly exciting. So the kind of key idea is that if the model is doing this kind of abstract analogical reasoning, it should be able to do this mapping even if we rotate the world, as long as we preserve the structure. So if I tell the model that this dark blue color is blue and this dark green color is dark blue, it should learn that getting greener is how it should realize the dark relation. And then when I tell it this light blue color is green, then it should infer that this light green color is dark green. And so we should expect good performance in both these original and rotated worlds. We should expect bad performance if we just shuffle up all the things, because now we've distorted the structure and the model can't make use of this reasoning. So I'm going to show results from just the hardest setting. And in the hardest setting, what we do is all of the training examples the model gets come from the same kind of subspace of the color space, or for the other domains. So it gets kind of anchor points for the primary and secondary colors, and then just a ton of examples of shades of red and pink. But then at test time, it needs to, for example, label this color patch as navy. And when we do this, we can see that in the random performances here in light blue and shuffled, it performs very poorly as expected. But then in both the original and rotated worlds, we actually see pretty significant gains over that random baseline. And these numbers are still not, they're not perfect. There's a lot of progress to be made, but they're highly indicative of kind of the right process happening under the hood in terms of this kind of mapping. And like I said, this is kind of our hardest case. So we can argue from this that the model has this kind of structure to its conceptual space that is basically the same as what it would have had if it had just been perceiving color directly. So I think, it would be valid to push back on this to say, well, maybe reasoning about RGB codes isn't really the same as perceptual reasoning, right? Because those RGB codes are actually arguably kind of a symbolic linguistic representation already of the raw perception. So what this succeeding on this task might amount to doing kind of advanced linguistic analogical reasoning, but it's not the same as perception. So in the follow-up work, we're basically trying to do the same thing, but where the input to the model isn't something like RGB codes, it's actually kind of a raw image encoding like pixels, like we would get in any of the models that we traditionally call grounded perceptual models. So here we have an image encoder. We'll look at several different image encoders. These are models that are trained to take as input an image, and learn some vector representation to do some tasks. So we'll look at a few different ones. There's, predict, like you can do object detection, image captioning, or various other self-supervised learning techniques. And then completely independently, we have a language model that's been trained on autoregressive language model, predict the next word. So if you just ask, this example is from GPT-3 as of this morning. If you just say, what are they doing with no context, it says they're playing a board game. So there's no relationship between these models or the data they're trained on. What we're going to do is first freeze the encoders entirely. So nothing is allowed to update within the models themselves. And then we're just going to train a linear projection from the space of the image and output space of the image encoder into the input space of the language model. So basically, it's going to get some kind of tokens where the image representation is kind of pretending to be a text token. And then we're just going to take this as context and ask the language model to continue predicting the next words. And in this case, we see the models is correctly predicting he is surfing a wave, right? And actually, when we do this, we see that we don't get any benefit to full multimodal training the model over just doing this linear projection post hoc into the space of the language model. And this is across a variety of these image captioning tasks and these visual question answering tasks using some different metrics. And so the last point I want to make is that I think you could push back even further. Many times these image encoders are trained already with some language in the loop. And I don't personally think that makes them not perception, right? But this could be kind of a point where we would say, well, this model might be trained on something like ImageNet. It's trying to detect objects in the image. Those objects are linguistic categories. So really this conceptual space that's coming out of the image encoder is already a linguistic conceptual space. And so maybe we shouldn't be completely surprised when it's able to project into the space of language model. But we can look at other self-supervised learning techniques that don't have any language in the mix. So for example, filling in patches of images. So there's no language here. It's really just learning the structure of the perceptual features within the images. This is a model called BEAT. And when we do that, we still see an impressive amount of semantic information is transferred. It is admittedly not as good as the models trained with language. So for example, here it messes up. It thinks that the tennis racket is a baseball bat, or that surfing is jumping into the water. But it's really hard to argue that nothing meaningful is being transferred between these spaces. Right, so that I will wrap up. So I think, like I said, I think there are multiple very compelling in principle arguments we can make about why the lack of grounding should not invalidate a model as a potential model of meaning. And I think Gary and David will talk more about these. I think we want to focus on the empirical results because when we're looking at the models we have now, they strongly suggest that something must be true in those empirical arguments because we're getting the kinds of models out despite a lack of grounding. And specifically, I think there's two main conclusions. One is that as it is right now, adding perceptual information doesn't improve models' representations of meaning according to our metrics. And we see that these models can be grounded post hoc. Right, thank you very much.
Next speaker is Brendan Lake. Okay, I don't know if that's your first one or not.
Everybody, I'm going to talk about building machines that understand words as people do. Today's large language models are amazing. I think there's no doubt about that. This is from the GPT-4 paper. Apparently, you can give it an image of one of the precursor papers to GPT-4 and ask it to summarize that paper from the JPEG, and it can do a reasonable job summarizing the paper, and you can even ask it about specific figures. This is clearly amazing, and getting to the question of today, that ability to perceive the visual world, look at an image, have other aspects of sensory grounding, is that needed for meaning and understanding? I'm a qualified yes on this question. It really does depend on the meaning of meaning and understanding. Ungrounded models learn a lot about word usage and the relations between words. That's There's no doubt about that. But by definition, they have no connection between text and the outside world. The traditional view in linguistics is this is critical to meaning, having that connection, that reference to the outside world. I'm a strong yes on a variant of this question, however. Do language models need sensory grounding to understand words as people do? That certainly is yes. And I've written a lot about this with my NYU colleague, Greg Murphy. We wrote a paper, Word Meaning in Minds and Machines, which is exactly about this issue. It was published in Psychological Review in 2021. And this paper goes on at length about a number of things I won't have time to discuss in this brief presentation, but check it out if you're interested in these issues. But one of the key things we get at in this paper is, what do people know when they know the meaning of a word, when they have the concept behind a word? So take the word umbrella. When you have this concept, and this is what we often mean in cognitive science by knowing the meaning of a word is a pointer to a concept, some mental representation of a category in the world that you have. And this concept supports a lot of different flexible behaviors. One type of behavior is describing a scene and understanding descriptions of scenes. So when you know the word umbrella, you can look at any of these scenes and you can talk about them, right, and recognize the umbrellas. And it's not that language models can't do this as well. Of course, those language models would have grounding. They have some sensory grounding. They have a visual encoder. And in the paper, we took a 2020 image captioning system and we put past these images through it, and it can do a nice job talking about them. Again, the system has grounding, like a close-up of a red and white umbrella, a woman walking down the street holding an umbrella, and so on. But these are the types of umbrella images that are readily available from Google image search and so on. And it's important to emphasize that just adding a vision encoder or just connecting it or fine-tuning it doesn't mean you're done. Human concepts are far richer, more flexible than that. And in the paper, we propose this ad hoc umbrella test because it turns out that animals in nature can actually construct ad hoc umbrellas. That when it's pouring rain, at least often enough for photographers to capture it sometimes, a frog will go under a large leaf or a monkey would hold a leaf above their head, or a toad could seek shelter under a mushroom. And of course, this isn't literally an umbrella in the sense that we understand the artifact of an umbrella, but you can make a very clear analogy to an umbrella, right? And you take the same system and you ask it to describe these pictures, and it's a bird perched under a bird feeder, a bird sitting on a car, a bird sitting on a branch. It actually mentions umbrella in one case. This was a 2021 system that was actually getting a lot of the animals wrong. You might say, well, okay, maybe umbrella doesn't come to my mind as like the first word when I see this. But below are labels from a strong object recognition system. And you can look at all the categories that it thinks are more likely than umbrella, which is one of its categories. So things like tree frog and lakeside and fountain and spider web and rotisserie are more likely than umbrella for these particular images. So it seems to be missing that ability to stretch the meaning, right? And so yesterday I looked at an updated image captioning system. This is Blip. And it's not obvious that there's been a lot of improvements on this particular test. You still get two frogs in the rain, a small bird in the rain, a frog with a frog in the water. It's getting the animals more right. And sometimes it produces kind of weird nonsense. You can go even further than this. People's understanding of a word is even more abstract and analogical. And this example was suggested by Melanie Mitchell. You could think about the American nuclear umbrella over the West, right? That's another use of the same concept, or an umbrella organization or umbrella insurance policy that provides you broader protection, or technology that falls under umbrella of a large language model, just to remind you how much we know when we know the meaning of a word. But what else do people know when they know the meaning of a word? In the paper with Greg, we provide this short anecdote of where you're at a dinner party and you're going to have a short exchange, just to remind us how many different facets and how grounded our understanding of words is. So imagine you're sitting down at this dinner party and you see this in front of you. And of course, you could recognize the various objects in front of you and the relations, and you see some food on the knife, and you remark, that knife is dirty, right? You're using this word knife in this particular way. And this leads to the first desideratum. Greg and I offer 4 desiderata in the paper that we think are necessary for models of human-like word understanding. The word representation should support describing scenes and understanding their descriptions, much like the umbrella case that we just talked about. So you say that knife is dirty, and then someone else at this dinner party might actually hand you a clean knife, right? Like the one that just appeared on the right-hand side over here. And this is the second desiderata. Word representation should support responding to instructions and requests appropriately. You hear a word and you can actually take actions in the world in response to that. And that's important. Well, I was hoping for a butter knife might be what you say in reply. That's not the type of knife you were looking for. And this leads to the next desideratum. Word representation should support choosing words on the basis of internal desires, goals, and plans. You have thoughts. Those thoughts are often things you want in the world, and you translate them into words. Right? And that's important that you have these things and you use your words to express them. And last, you might say if you're teaching your kids how to set up a place setting, forks go on the left, knives go on the right. And you'd hope that a short phrase like this, a short sentence, would help change one's belief about the world based on linguistic input. You actually learn something about the world, and that's the fourth desideratum. So how do I think about these things? It's not that AI systems must have all these human-like abilities to usefully model aspects of human-like word meaning. They're already useful models in a variety of ways, but human-like word representation should provide the basis of carrying out a variety of different flexible behaviors, physical, verbal, and mental, that rely on conceptual representation. And text-based models and lacking connection to the outside world do not support several of these abilities, and it's a non-trivial enterprise to extend them. It's not the case that you can just hook up a couple of encoders and expect it to understand a word like a person does. But to be clear, there's been genuine progress in all of these areas, and machines continue to march closer. I just want to quickly mention a little bit more about the other desiderata. So the second one was word representation should support choosing words on the basis of internal desires, goals, and plans. I think this is critical, and it's not controversial that large language models don't really have their own desires, goals, or plans. That's not how they're designed. They're designed to respond based on patterns and text in a way that is useful to us. And I just went straight to the horse's mouth here and asked ChatGPT, do you choose your words on the basis of internal desires, goals, or plans? And it said, I am an AI language model. I do not have internal desires, goals, or plans of my own. I'm programmed to generate responses based on the input I receive from users. And I have algorithms that analyze the input and generate responses that are most relevant to the input and context. So I'll just take this at face value, and it seems to agree. A word representation should support responding to instructions and requests appropriately. This is also something that language models can do in principle and in practice. We've done work on this in my own lab, where you can take a language model that, say, can respond to a particular instruction, and you can hook up a state encoder, it might be a vision encoder or something that looks at the state of a little grid world where the agent is that pink triangle, and then have another language model that's going to produce this actions in order to respond to the instruction. There's lots of variants of this. This is the particular variant that we tested in this 2020 NeurIPS paper. This is led by Laura Ruiz, who was a former student in the group. And she proposes this grounded scan benchmark, which is basically testing the flexibility of the understanding of these words that you have to act on. And what Laura found was that instruction models can struggle to learn abstract, flexible meanings of words like walk. So she trained the system to walk to various targets in all possible directions except targets to the southwest. And then at test time, it completely fails to go to targets in the southwest of the grid, because it was never trained to do so. And our meaning of walk is obviously very different than that. They struggle to learn abstract, flexible meanings of words like small and large, in the sense that you could train the system to go to a large red circle or the small red circle, and a particular size red circle is always the large one because it's always paired with something smaller. But then at test time, for the first time, it's now paired with a larger red circle. And now it's no longer the large one, it's the smaller one, right? And the model doesn't get this at all. It goes to a random red circle and it's not learning that same type of relational representation. Again, it's not that these models can't do this, but it doesn't seem to, they don't have the right sort of inductive bias to do so. Another word we looked at are adverbs like cautiously. So you can train the system to move cautiously, like to look to the left and to the right before crossing the street, before making a movement. And even with 50 examples of going certain places cautiously, it doesn't generalize well to new places or to new targets. Just to say a word about Desideratum 4, word representation should support changing one's beliefs about the world based on linguistic input. Do large-scale language models have consistent, genuine beliefs? This is also something that is largely understood, that they are not consistent in their beliefs, right? That they're not designed to be so. What we tested in the 2021 paper is we looked at BERT at the time and looked at it, whether it had seemingly true beliefs, even just for basic facts, like is a dolphin a mammal or not? And we found that minor differences in the wording would change the answer of the system like BERT. So if you ask, are dolphins mammals, or what type of animal is it, in various different ways, you get different answers, like mammals, birds. Dolphins are mammals and dolphins are a fish if you ask about the singular version of the noun. Now, to give credit where credit's due, yesterday I was trying this with ChatGPT and I could not get it to give the wrong answer for dolphins being mammals, even with misleading prompts like dolphins are my favorite type of saltwater fish, and it would very politely correct me. So at least for such a common fact like this, there's been genuine progress. But nevertheless, aiming for true human-like beliefs, I think, is very important. So to conclude, text-only systems can do amazing things, but to understand words as people do, their representations must be based on information that makes contact with the world and can be used to talk about actual things in the world. It's non-trivial, but highly worthwhile enterprise to develop word representations that can flexibly support the 4 desiderata that we talked about in the paper, and models that understand words like people are a higher bar worth reaching for, especially if we want machines that genuinely understand us and that we can have more fruitful interactions with. Thank you.
The next speaker is Dave Chalmers. One of the sponsoring organizations is the Center for Mind, Brain, and Consciousness, of which Dave and I are the co-directors. Forgot to say that earlier. Let's see now. Okay, here you are.
Okay, thank you, Ned. I will start with some ancient history. Back in 1990, Stephen Harnad named the symbol grounding problem. He looked at AI systems of the time, looked at the symbols, they look kind of meaningless. He argued that they have to have some kind of sensory grounding to have meaning, or perhaps some kind of bodily grounding in the body and in action, perhaps some kind of external grounding in the environment. Interesting relations between all of those. I'll focus especially on sensory grounding here. Fast forward 3 decades. We now have a number of people echoing this kind of criticism for current language models. They're potentially meaningless. They need to be grounded in senses and the environment. Emily Bender and Alexander Koller, perhaps most prominently, have argued that language models lack sensory grounding and don't have meaning or understanding. They're what Bender later called stochastic parrots, illustrated here. This is actually a debate with a slightly longer history in philosophy, where there's been debate for a very long time on whether humans require sensory grounding for meaning, understanding, and thinking. For example, Thomas Aquinas, back in the 1200s, famously said, "There's nothing in the mind that wasn't first in the senses." If that's right, it looks like thinking and understanding require sensory capacities, at least in humans. Actually, Aquinas made some exceptions for angels, for God, which already makes you wonder about whether things might work the same way for AI. Later on, in the 18th century French Enlightenment, you had figures like Diderot and Condillac, who advocated the view known at the time as sensism, which held that sensing, perception, was really at the foundation of all of cognition, no cognition without sensory perception. On the other side, though, there's been a consistent voice on the other side of this issue. One of the prime contributors was Avicenna or Ibn Sina, back in the 11th century, argued that in principle, there can in fact be thinking without sensing. His most famous route to this was actually a philosophical thought experiment, the thought experiment of the so-called floating man, who kind of appears in the sky at a certain time, has no senses or sensory capacities, but still is aware of his own existence. So he said, the floating man was created as a stroke, fully developed, but was not able to perceive the various things, preventing any perception. There's no doubt that he would affirm his own existence. And this was meant to be an example of thinking. Floating man can think about himself without ever sensing, and arguably without sensory capacities, although it takes a little bit more work to elaborate the experiment in that direction. Others argued that the floating man could think about all kinds of things without having senses. He could think about mathematics, he could think about logic, he could think about philosophy, perhaps he could hypothesize at least about external reality, about other minds, even perhaps about scientific theories of the world. If that much is right, it looks like thinking and understanding don't absolutely require sensory capacities. It's at least possible in principle in some systems to have thinking and understanding without sensory capacities. That said, it's a somewhat limited conclusion. It certainly looks like some sorts of thinking and understanding may require sensory capacities. Just think about, a pure thinker, a system without senses, like Avicenna's floating man. It's arguable that a seeing without senses couldn't fully understand, for example, the experience of the color red, something deeply sensory, or likewise things which are deeply bodily, like knowing how to ride a bike. Could a system without a body know how to ride a bike? It's very unclear. Arguably, these systems could have a system without senses could have a partial understanding of these things, perhaps analogous to, you all know the thought experiment of Mary, the scientist in a black and white room, who knows an awful lot about redness, has a scientific structural understanding about redness, but still in some sense doesn't seem to understand its intrinsic nature. I would argue that a system without senses could have these kinds of partial structural understanding of these things, even if not a full understanding. And likewise, I think for AI, perhaps even more clear for AI than for humans. An AI system without sensory input, there's no obvious obstacle to it being able to think about itself, to be able to think about mathematics and logic, for it to form at least hypotheses about the external world, and for it to have at least this kind of structural understanding of many aspects of the world. At the same time, there would be limits on its understanding in sensory and bodily domains. Would I have a full understanding of, say, sensory kinds like color or embodied knowledge? I think you could make the case that it would have merely a limited understanding of those things. Which brings us to language models. I think much of what I've said applies in principle to language models, at least for thinking and understanding in general. In language models, that does not require sensory grounding. So I guess I'm on the record. My answer to the question of the debate is no. On the other hand, some sorts of thinking and understanding, I would argue, do require sensory grounding. So that's why my answer in the debate is no, but it's complicated, like most things. For the second half, I really want to focus on a slightly different question. Not does thinking require sensing, but does sensing somehow boost thinking to a new level, both in language models, and it's a question that arises for, for humans and for intelligent creatures generally. Here, I think it's useful to compare and contrast pure language models with multimodal models, as Ellie has already done. Pure language models have text inputs and outputs. It's an interesting question whether that should be regarded as a sense. Maybe it's a sense of a very limited kind. It's certainly a connection to the environment. It's not a human style sense, but multimodal models process information much more reminiscent of a human style sense, images, audio, and so on, and could even have quasi-embodied outputs controlling a physical or virtual body. So here's Google's SayCan. It processes, visual information about the world and controls a robotic body. That's a multimodal model. It's clear that multimodal language models have some capacities that pure language models lack. At the very least, the capacity to sense in these ways, the capacity for bodily action. Somewhat more controversially, at least if you think that these models can have mental states at all, maybe they have some low-level form of perceptual understanding, some form of embodied know-how. But the question really, the crucial question I think for now is whether multimodals, how they compare to language models on the domains and tasks that they share. For example, do multimodal models outperform language models on text-only tasks or on tests of cognition and reasoning? I think I think everyone's, certainly my expectation 10 years ago before language models came along was surely the answer will be obviously yes. Multimodal systems will just be vastly better than pure text systems at this. That pure language models of the kind which are ubiquitous now may be good for modeling language tasks, but not, no reason to think they'd be so successful for modeling thinking and reasoning. And I think it's really worth noting just how surprising the development of language models has been. Now we have these pure language models that seem to excel at all kinds of non-linguistic tasks, showing at least hints of what some people see as general intelligence. Multimodal language models, as Ellie pointed out already, sometimes have a small boost, sometimes very little. Here's a bit of data from the recent GPT-4 paper where you've got GPT-4 doing way better than GPT-3 on 1 million standardized tests. But they test the version with vision and the version without vision. They're typically just about the same. Occasionally the version with vision does a little better, but only a little. Here's a nice little illustration from last year, a discussion that Jan and I had on Twitter about 6 months ago. We were talking about whether these systems have world models, and Jan said, no, look, for all kinds of embodied things that require sensory or embodied knowledge, they'll do badly. Can a language model figure this out? In front of us are 6 gears, 1 to 6 on axles in a row. Each gear is engaged with the next gear. If 3 is rotated clockwise, what happens to 1 and 6? Well, I tried it for GPT-3, and Jan was right. GPT-3 made a mess of it. It did wrong. Another model did a bit better, but messed up consistency. But that's it. I'm holding out for better performance from GPT-4. So I thought it was time to check in on that prediction. And I ran GPT-4 on this yesterday. And well, to cut a long story short, it totally nails it. Gear 6 goes counterclockwise. Gear 1 goes clockwise. So there you go. This does not prove anything, but it's but I think it's nonetheless illustrative of something that we're seeing left and right these days, where so many of the things people say these language models can't do end up being done. Multimodals, I think, nevertheless, are clearly valuable. A picture's worth 1,000 words, people say. Image training, images carry data that a simple bit of text doesn't. But if, on the other hand, enough corresponding text data can match the performance of a multimodal model, then it looks like sensing is not boosting the thinking to a new level that can't be reached without it. Okay, I just want to say so these results, I think, are unexpected and at least provide some evidence against a strongly sensus view of cognition, where it's essentially grounded in the senses. I finally want to say something about this question, which is not the topic of the debate, but hovering in the background. Do large language models, in fact, understand? I think to answer that question well, we may need some of what philosophers call conceptual engineering, where we engineer new concepts of understanding thinking meaning, not just software engineering, new models, but actually new concepts. I mean, for example, here's one useful distinction. What I'll call B understanding is to behave as if one understands, whereas E understanding is to experience as if one understands. I mean, many, many more distinctions could be made, but this is about performance versus subjective experiences. Arguably, current language models may B understand to a reasonably high standard, but they don't E understand. They don't have the subjective experience. Beyond that, you might ask the question, do they really understand? I think at some point, this becomes a verbal question. Okay, so I will, moral understanding AI capacities requires not just software engineering, but conceptual engineering. Oh, I had a wonderful ending slide that didn't show up here. But I think the final moral was, do language models require sensory grounding for thinking and understanding? Yes. Sorry, no. Do they require it for some sorts of thinking and understanding? Yes. Does sensing give some kind of fundamental boost to thinking and understanding in language models that couldn't be had without it? No. Do current language models, in fact, understand mu? Thank you very much.
Okay, our next speaker is Jacob Browning. Let's see, here's your slide. Where are they? Here they are.
So in 1966, MIT's Summer Vision project aimed to teach a computer to use to see in a 3-month program. There was a broad assumption that getting a computer to use language and reason was the hard problem of AI. Perceiving, by contrast, was thought to be a simple, nothing more than putting inputs into a cognitive system. This project failed. It turns out that vision is really hard. But for our debate today, it's worth exploring the historical background assumptions underlying the vision project, specifically the idea that cognition is essentially linguistic and the corresponding assumption that non-linguistic processes like perception, action, emotion, and so on are all non-cognitive and should be easier to solve. I needed that slide earlier. It is ironic that in the 20th century, philosophers came to assume that cognition is essentially linguistic because for much of the modern period, as Chalmers just noted, perception was the dominant model of thinking. Understanding something meant perceiving it clearly and distinctly in one's mind eye. But Kant recognized a problem with this view. Although some thoughts, such as which hand is left or right, depend on perception, there are other thoughts concerning freedom, necessity, causality, or logical inference that depend entirely on language. Kant argued that the laws of logic, physics, and ethics can only be expressed propositionally as assertions or rules. For the logicists, at the end of the 19th century, this led to the claim that all thoughts are propositional. Natural languages for these thinkers are just the way we clothe propositions. Cognition is linguistic, ideally expressed in symbolic logic, but natural language does in a pinch. If all thought is linguistic, then there was a short step to saying all knowledge is linguistic. The assumption was that the totality of thought just is a massive list of all the possible sentences of language. This led to claims that for these thoughts and languages to be humanized, they needed to be grounded in our experience, in the specific physiology and sense modalities of human beings. Rudolf Carnap provided the most ambitious version of this view, a logical construction of the world, translating the whole of perceptual experience and the knowledge based on it into sentences, so that everything knowable by humans could be expressed in a logical format. This is where the hubris behind the AI researchers at the Summer Vision project came from. The thought was that Carnap had already shown how to digitize the world by putting it into logical senses, such as defining all colors by their location in 3-dimensional color space, sounds in terms of their pitch, volumes, and timbre. This took them to believe that all perceptual knowledge could be expressed linguistically, allowing us just to read off the relevant information from the logical sentences. But the project failed Because success in artificial formalizable domains, like recognizing how different red is from blue by measuring their distance and similarity space, had little to do with actually recognizing a face from pixel values, much less understanding what that face is trying to represent. Understanding a face as a series of sentences of pixel values does not help with the content of what the face expresses. This requires interpreting the pixels as edges and relative locations, which can be interpreted as features, as objects, as events, and so on. In short, building up a full visual system to interpret it. The takeaway of this project was that while some thoughts are expressible in language, not all thoughts are. Linguistic representations excel at representing highly abstract relationships between universals using variable binding, composition, and discrete symbols connected by rules such as the subject, verb, and object rules, or the logical rules of inference. Many linguistic sentences, such as laws of nature, simply cannot be represented in any image. How could you, for example, picture necessity? But the reverse is true as well. There are other kinds of representation with their own unique quirks. Imagistic representations convey a lot of information by passing on some dependent variables like red, green, and blue values along some independent variables like the spatial coordinates of each color. This allows the dependent variables in an image to express things like shapes, sizes, relative locations, edges, surfaces, movements, interactions, and so on. These representations work by isomorphism. They represent because there is something similar between it and between the representation and the way the world is. This allows for detailed information about the world, but it is difficult to picture abstractions like justice or freedom without resorting to symbolic representations. But seeing or hearing something in the image relies on another kind of representational format, the skillful know-how encoded in distributed representations, such as those found in neural networks, both biological and artificial. The crux of these systems is forming a statistical model of the domain it is representing according to the function the system is trying to compute. Put more simply, in a visual recognition system, the network aims to come up with a representation preserving the essential features of the domain for predicting the class membership, and then compressing and ignoring the information that isn't helping with the predictive task. These systems, of course, have their own limitations. Specifically, they are continuous, not discrete, and struggle with the strict rules that underlie linguistic representations. They do well on know-how, but less well on propositional knowledge and knowledge that. This leaves us with three different kinds of representational format: linguistic, imagistic, and distributed. The logicist program overestimated the universality of the linguistic format, ignoring its many limitations, and underestimated the importance of the other two, both imagistic reasonings and know-how. This brought with it blind spots. It ignores animal and infant cognition, for example, imagistic reasoning, skillful know-how, and evaluative states like emotions. Either assume these could be assimilated to linguistic representations, or more commonly, simply denied that they are representational at all and downgraded them to non-cognitive states that are not properly part of a thinking system. It's worth noting, though, that some alternative approaches from the same period, such as the pragmatists, went from the opposite direction and assumed the non-cognitive aspects on the logicist picture were actually the heart of cognition. Pragmatists argued cognition was grounded in action and prediction, perceiving it as not a passive stimulation, but as categorizing the world into what matters, what is liable to lead to pleasure or pain, and skillfully responding so as to preserve oneself in a hostile environment. Among those inspired by Darwin, this was seen as part of the evolution of life on Earth. The know-how for integrating perception into action evolved in tandem with more complex imagistic representations and evaluative states, and more sophisticated behavioral know-how for categorizing, predicting, and simulating what will happen next. This approach often also provides a different model of language, not primarily as a tool for thinking and storing knowledge, but instead as a piece of social know-how, a tool for communicating between agents. Communication in these cases depends on background knowledge. It is really easy to pass along a complex signal in a few words if you and I have a lot in common, and really hard if we don't. For the pragmatist, language arose as a method for coordinating behavior, one that rested on enormous amounts of background knowledge, similar embodiments, upbringings, skills, cultures, and so on. And the more in common, the less that would need to be said out loud. This second model suggests that language-only systems will possess only a shallow understanding for good reason. That's what language is for. Language is for capturing the high-level abstract information, not the nitty-gritty stuff we can see and do and interact with, the stuff we're all supposed to know. Language rests on interlocutors already possessing the deep multimodal embodied know-how for successfully navigating the social world and the social awareness and reasoning needed for joint action. Language certainly isn't limited to context-sensitive communication, obviously. As human culture evolved, we recognized we could do more with language. We could transform it first with storytelling and then with writing into a context-free medium, one now idealized as symbolic logic and programming languages. This allows us to store massive amounts of information and learn complex rules, passing these along through the generations error-free. This is what the logicists got caught up in and led to fantasies of a general encyclopedia that encompassed every possible fact in an utterly unambiguous, rigorous, fully explicit way. But this was overambitious. Even textbooks and encyclopedias depend on their readers possessing a background understanding and broad capacities to understand different kinds of representations. That's why they're filled with pictures and diagrams and involve practical exercises. The takeaway of the second model is that a lot of knowledge is bound up in understanding and utilizing imagistic representations and embodied know-how. We can call this pragmatist approach the engineering model, where cognition involves solving everyday problems requiring intuitive physics, biology, and psychology, as well as social knowledge and the skills for using whatever tools are at hand. This strikes me as a far more plausible model for understanding and a better path to a more capable AI. It also clarifies why building a self-driving car and succeeded at open world games like Minecraft have proven to be extremely difficult. But building a successful chatbot has amounted to just a scaling problem. It also explains why language models are so great at linguistic tasks like writing poetry, but fail embarrassingly on the simple kind of engineering problems that children perform effortlessly. This suggests that linguistic understanding is an important but limited part of a broader multimodal intuitive understanding of the world. It's a tool, a piece of know-how that expands our social and cognitive capacities immensely. In humans, linguistic understanding presupposes and depends, however, on an older non-linguistic understanding. If we're looking for a machine with human-level intelligence, even the understanding of a linguistically simple 2-year-old, we should look beyond large language models.
And our last speaker is Gary Lupian. There you go.
Okay. A week ago, I posted a survey on Twitter and Facebook. We had about 170 full respondents and mostly CogSci people reflecting who follows me, I guess, many linguists, some machine learning and CS folks. And on many questions, there was quite a bit of consensus. Can large language models think? Most people definitely not. For the question closer to the topic of this debate, I have to commend the organizers. There's a really nice split. People really disagree, and you can ask this question in various ways, and people are somewhat consistent, but you keep getting this kind of split. It's impossible to derive true word meanings only from observing how the words are used in language. Okay, so people disagree. I want to very quickly address one of the elephants in the room, which is that, of course, there is a kind of indirect embodiment because we, the producers of the language on which these models are trained, are embodied agents. But that's a different question, right? So could these language models or models of this sort create meaning, right, without us? At this point, I think clearly no, right? But the question is about, do large language models need their own sensory grounding for meaning and understanding? And so I think we need to start by saying sensory grounding of what exactly? Language is not one thing, and there are many kinds of words. For example, there are words like this: apple, swan, table, jump, concrete words. And then there are, it's a continuum. There are abstract words. And typically, when people talk about abstract words, they think of things like freedom and democracy. And we've argued that this actually marginalizes the importance of abstract words in language, because you can say, well, kids don't talk about freedom and democracy, and even adults, like, that's not normal day-to-day conversation. But there are many words that are, in fact, as rated by people, much more abstract than a word like freedom. Fun, idea, trouble, imagine, enjoy. All of these are, in fact, words that kids use, words that are very much a central part of language. Agree, nevertheless. What is the sensory grounding of nevertheless? Okay. Some of you will be familiar with this. So this is a widely used set of norms, concreteness norms. It's interesting. This is used very widely in psychology, also in machine learning. Words that are rated on the scale from most abstract to most concrete. It's interesting if you actually look at the original paper, what the raters were asked to do when they're rating the words. So on the concrete end, they're asked to think about word meanings are concrete to the extent that it's something you can point to or enact, right? Like you can convey jumping by just jumping, okay? So if that's the kind of word it is, rated as concrete. If it's a word whose word meaning we know because it can be defined by other words, that is abstract, okay? This is what the task these folks are doing. And so here is freedom, okay? These are the top 8,200 English words. There are a whole lot of words, fairly frequent words, that are more abstract than freedom. And these words are used by these small language models. Okay, so here's an example. This is Finn, he's 2.5, while listening to a song. These are all words that he's at the time saying, okay? So he is doing some metacognition here. What worry mean? What wrong mean? What somewhere mean? Okay. He says, I love you too. What to mean? Or he's not a good friend. That's his brother. He telling me I'm yucky. Getting ready for school in the morning. Or he's been a bad example, not putting his jacket on. I'm telling him, come on, jacket on. Or he's been a bad example. I want to be a bad example too. Okay, so this is child language. All the words in red are more abstract than the word freedom. Okay, what is the grounding of these words that kids are using in reasonable ways? And I think we would agree that they have meaning, even to these young children. Now, Brendan used an example from his wonderful paper of these images and how somewhat grounded models, but still, right, models, this was an example that these models lack the kind of extended understanding that our own concept of umbrella has, okay? Right, so we might label these as an umbrella, but the models don't. Well, what is the concept of an umbrella in an ungrounded, but a larger language model? So I asked, this is ChatGPT 3, imagine you're a small bug in the forest, it starts to rain, what can you use as an umbrella? And it sort of like describes a lot of these types of images, right? All these things, mushroom, leaf, grass, totally ungrounded. It then gives a bit of advice. It's important to find shelter quickly, okay? So I'd say that, okay, maybe it can't identify a weird picture of an umbrella, but this is much more central, right, to the concept, to human concept of an umbrella, and it's getting this from language alone. Okay, this is from a recent paper, preprint under review in BBS from Mahawald et al. And they want to, the point they're arguing here is that the knowledge in these models, in part because of lack of grounding, is again kind of limited. And the GPT response in this paper they're citing was their responses were rated by other humans and compared to human responses, and the human responses, especially in these more constrained versions of the prompt, are better, okay? But consider all the implicit knowledge, actually, that these responses, imperfect as they are, have, right? So this language-only model has a notion that roofs are up high, right? That if you saw a sofa, it gets smaller, right? That ordinarily a sofa doesn't fit through a window, right? And this is how does it know this, right? Because it is embedded indirectly in ungrounded language. Okay. This point here is very similar to one made by Ellie, that my own expectation when I did this analysis back in 2016 or 2017 was that because people are bringing a lot of grounded knowledge to bear on various semantic judgment tasks, for example, similarity judgments between words, correlations between human responses and responses based on word embeddings should be better for more abstract concepts, for which both the models and the humans are depending on linguistic relationships, than for the more concrete ones. And in fact, you just don't see those differences. So the correlations in this data set and other ones that I don't have time to show you are just, it's flat, it's similar. So if people are bringing certain concrete sensory knowledge to bear on what they think a relationship is between two words, the models are doing somewhat similar things, right, without having that direct embodiment, because many of those sensory relationships are embedded in language. When kids, so this is a 5.5-year-old, when kids often talk about concrete words, what does concrete language of kids looks like? Some of it is, where's my fork? Okay, but some of it is like this, right? Planets, the sun, the moon. We might say these are concrete concepts, but clearly the meaning of a phrase like this is deeply relational, right? And the point I'm trying, the larger point is that a lot of the language we use, right, is not really, it's the meaning, the core meanings are not really about, right, the references to external things. Real external things. Okay. What about words like this? Grounding of perceptual word meanings. Words like glistening, transparent. Surely we need embodied sensory knowledge to really understand this. This is one of those other questions that has a bimodal split. A person born blind cannot truly understand the meaning of the word glistening. Some people yes, some people no. In fact, there is reason to think that blind people do have not identical understanding about these kinds of meanings, but fairly deep, sophisticated understanding of meanings of concepts like glisten and transparent. So here's the correlation, semantic judgments between congenitally blind people and sighted people. It's pretty strong. Both of those judgments are correlated. We see this for many different tasks. About the same with word embedding models. Okay, and all right, what about, okay, so those are, how similar are these words? What about just more open-ended tasks? What does a blind person know about transparency? Another question, a word like transparent has certain metaphorical meanings, and some people think that, well, okay, sure, those kinds of meanings, someone who's blind can understand perfectly well, but the visual meaning, you have to actually be able to see. This is Tommy Edison. He was born blind. He has a lot of wonderful videos. I can't show you video because of this format. So I'll just tell you what he says when asked about transparency. So he begins by saying, what I know about transparent things is that light can pass through them. You can see through it. People talk about, my presidency is going to be very transparent. That means you'll be able to see right through it and know exactly what's going on. Okay, so that's metaphorical. What about the more perceptual side? So what are some things he's asked that he knows, or things that are transparent? It says a window or a piece of glass you might drink of is transparent. You can see right through that. Saran wrap, kind of stuff that you wrap food with. Glass shelf in the refrigerator. Water too. You could look through water if it's clean water. Where did you learn this? Says, I think I learned a lot of this in school, like in science class and stuff, but also from everyday life, from people being in cars and, oh, would you look at that? Person is doing in that other car. For example, the water, how many times have I been to the beach and people say, look, it's beautiful. You can see right through to the bottom. And he says, I don't really know what it means to be able to see right through something. In other words, when you look at something, do you see the window and the thing, or do you not see the window? So if you're looking out of a car window in another car, do you see the car window as well as the other car, or just the other car? See, that's the kind of thing I don't know. Okay, so of course there are differences, but we wouldn't want to say that when a blind person talks about transparency, it's just a stochastic parrot, right? Or a parrot of any sort. So children's earliest language, it is true, is heavily grounded. It's also arguably the least meaningful language. As kids start producing more meaningful language, it becomes very quickly incredibly abstract. That's it. Thank you. That's all. Do people get to vote? Vote no.
Stay here, stay here. Okay, will the speakers come up? Okay, so we're going to have a brief panel discussion and then comments from the audience. While people are filing in, I have a question for the panelists. You know, Jan raised this issue that I find very interesting, which is these large language models have a window of text and they predict the next token. They don't plan 10 tokens ahead. And of course, as the window gets larger, it'll look more and more like they're planning many tokens ahead. But I guess Jan was saying there's an in principle difficulty here. Anybody want to speak to that? That was your point.
You were pointing to someone else, yeah, I think there is a fundamental difference between producing reactively one token after another and the ability to plan. In the first case, in a large language model, but also in sort of the type of tasks that humans do subconsciously or without sort of using all the power of their frontal cortex, the amount of computation that is used to produce each token is finite and limited. So in a large language model, for example, to produce one token, you have to basically propagate the signal through a fixed number of layers of some giant neural net, and then produce a token, and then do it again, produce a token. So it's fixed. There is no ability for the system to think longer or shorter. It will spend the exact same amount of computation to produce every token. Whereas, of course, when we reason, when we think about things, complicated things, we think about them longer. And it's probably indicates that we have this process by which we elaborate an answer that is not purely autoregressive with a fixed amount of computation. From the theoretical point of view, theory of computation, the idea that the number of different functions that we can represent with a fixed number of computational steps is very limited. Whereas the set of functions we can represent through the optimization of some objective is Turing complete. Okay, so on the one hand, system one autoregressive production, we're limited by the number of computational steps that we allow ourselves to use. In the second case, we have essentially Turing complete power. So I think there's a fundamental difference between those two things. Autoregressive LLM to system one. We need to build systems that do system two if we want to reach anywhere close to human intelligence.
So does anybody want to respond to that or raise some other issue?
Can I respond?
Yeah, go ahead.
Yeah, so I wanted to say two things on this issue. One is, I think it's debatable whether large language models are always going to use the exact same amount of processing for every token. So if we have some studies, and I've seen other studies to this effect where, for example, for transformer language models, you can effectively decode at every layer and treat it as a language model. So you can say how early in the forward pass did it commit to this as the next token. And for very easy predictions, it commits right away. And for harder ones, it takes until the very end. And you can even see that in some of this stuff with like chain of thought reasoning or something, you can play that out beyond the actual weights of the model. Then it can attend to its own outputs and it can play out this computation even longer. So I think you see kind of the early versions of what could eventually be like arguably a longer reasoning process. And when the model knows right away, it knows right away, and then it just passes that thing right along through. But I guess this came up in a lot of the yes answers, and I wanted to ask for more clarification because I think the subject of the debate is, do you need grounding for meaning. And then a lot of the arguments focused on things that had to do with like weaknesses of like things like sample efficiency or reasoning, or things that really seemed like more criticisms of neural networks, whether or not they're grounded. So I didn't actually see the connection between why reasoning abilities directly weigh in onto the kind of grounding and meaning question, like per se. So I was just wondering if there was kind of a clearer connection to be made between the evidence that models sometimes mess up on reasoning tests and the need for grounding.
I think the quick connection there is that for grounding to be useful, we need systems that can learn word models, that can predictive models that allow them to, and that's a necessary component to allow planning. So planning would be a consequence of being able to run word model, and word model is the tool by which grounding occurs.
So anybody, yeah, go ahead. You can just speak, you know, you don't have to wait.
Right, and to add to that, I mean, the examples that I talked about that relate to reasoning is on the basis of this cognitive science view that a word is a pointer to a concept, and what's so important about our understanding of words and when we acquire concepts is that we can use them for reasoning, we can use them for multiple tasks, we can speak about them abstractly, we can recognize a very concrete example of it. And while I'm at it, I should respond to Gary's clever use of GPT-3 to ask about the umbrella. And I mean, that was touche, that was a nice example. I do think it's interesting how patchy our technologies are. You ask the same question or related question one way, you ask it in another way, in another modality, and you get a completely different answer or a different failure. And this could be suggestive that we don't know yet the right way to do multimodal learning and to truly link these things together. We're going to have to look for some new examples in the sense that it's so hard to know what these systems have seen or what it hasn't. I mean, I would wager that GPT-3, GPT-4 have read plenty of novels that have talked about people getting stuck in a rainstorm in the forest and have can seek shelter, right? So we'll have to find some true examples of a very idiosyncratic generalization.
And as the final yes, I guess I'll just speak real quickly. Generally in philosophy, meaning is maybe a lower bar, but understanding is usually taken as a very high bar. It does usually require kind of broad reasoning capacities. So it is usually assumed that like if you can use a word successfully, that's a low bar, but if you can also make predictions about how it'll work in various engineering situations or problem solving, then it's more like you actually understand it and are not just kind of succeeding on the statistical task.
Yeah, I hear that, but I guess I'm still failing to see why the failure of image captioning models is a data point in favor of models needing grounding, especially when the text-only models, like if we're asking about models without access to grounding, really the only relevant data is the success of models that only have text. And so the success of GPT-3 on that seems like the only relevant data point. So I think I'm just failing to see why the failures of self-driving cars and image captioning models factors in.
Oh, I was just going to add that the bar for understanding is certainly higher, but by that bar, we humans fail all the time. Where we talk about things that we don't understand, we talk about things, and we trust each other that talk is meaningful, right? And our knowledge is patchy, right? I think one reason why it's not as patchy as some of what the examples are showing large language models have is that we want to be consistent as agents. So if you ask a question one way and you give a response and you ask a question a different way, one reason why you don't give a different response is that you remember what you just said and we have a bias, unclear where it comes from, right, to just be consistent. But if you look at a lot of memory experiments, for example, can a person retrieve a memory? Totally depends on the retrieval cue, totally depends on context. So if you can do it in some context, one would think, okay, the knowledge is there, right? But if you can't access it, to what extent, right? Is it Like, is it being there the point, right? We too are very, very context dependent.
You could also argue, like we were saying, language models don't have goals, but they do. It's to predict the next word. And so from the model standpoint, it might very well know that dolphins are mammals, but it's confused about what is a plausible next sentence. And it thinks that the probability of these other words in the sentence factor into that. It's clearly like wrong, as in a human wouldn't give that behavior, but I don't know that it's evidence of not meaning or understanding. And in fact, it might actually be the thing you would expect a model to do if its goal is to predict a plausible sentence that appeared in its training corpus.
Fair enough. That is very much the goal of those models. Is their singular focus, right? That is the only thing they care about until you at least do reinforcement learning with human feedback, and then of course you're bringing in all these other aspects of what is valuable to us as people. But I guess that these points about the fact that our use of words is so closely linked to our goals and our thoughts and what we want to say, or our use of words are so closely linked to looking out at the world and describing something, is to respond to an argument that you can make that the language models may not have meaning in exactly the way people do because they don't have sensory grounding, but it's really close, and like the vector is like right in the right spot, and all you have to do is attach a camera or attach a goal, and it will work, right? And it's basically a complete theory of word meaning as it might relate to a person. And it works better than I would have thought. I mean, it's extremely impressive, the example that you showed, where you can just learn a linear transformation and all of a sudden get a language model to talk to a vision model without doing any future learning. But I see those examples as pointing to how hard it is to understand words in all the ways that we do, and to get those edge cases right, and how abstract our concepts and use of words can be.
So to elaborate on some of the things I was just talked about, I think when the absence of goal, there's one goal that autoregressive LLMs have, and it's indeed to predict. And so you cannot separately control the task that the LLM was fulfilled by any other way than by changing the distribution of training samples that you train down, or by changing the prompt. Those are the only two things that will influence the response. You cannot specify the goal other than by engineering the prompt. Whereas we as humans have many ways of defining goals or objectives for ourselves that are not necessarily defined linguistically, first of all, and that we can elaborate answers that do satisfy those goals in ways that LLMs can't really do. One problem with autoregressive LLMs is that there are three different tasks, really, or three different modules that should be separate. One is the sort of predictive world model, what's going to happen if I say something in the mind of the person I'm talking to, for example. The second one is the goal of the task. And the third one is generating fluent text. And in an autoregressive LLM, those three capacities are all smooshed into a single genetic network that is only influenced by the statistics of the training set. Now, when we accomplish multiple tasks using different goals, our world model doesn't change that much. We're still living in the same world. And so if we had an architecture by which the world model was independent from the goal, and we could change the goal, we would have a system that is much more general, because we can dynamically change the goal without retraining the system. We cannot do this with autoregressive LLM. We have to retrain them.
Why doesn't
I
the,
think it might be time to have some questions from the audience. Rosa? Loud, stand up and loud. I think it'll be useful to identify yourself.
And I just wanted to ask everyone to clarify what they mean by grounding, because I don't think you all mean the same thing. Like, I think in some cases you mean like causal interaction with the world involving action, like maybe Brendan meant that, whereas other people seem to mean just has input in different formats that seem more close to the kinds of perceptual inputs that we get. So I was just wondering if you actually agree about this.
Did you hear in the back what the question was? The question is, what do you mean by grounding? There are two different things. One is the inputs to the system. What was the other one? I've forgotten.
Causal interaction.
Oh, causal interactions with the world. Yeah.
I briefly identified three kinds of grounding at the start of my talk. Sensory grounding, bodily grounding, and external grounding. And I do find, yeah, that the word is used in all three and more of these ways in this debate. For the purposes of my talk, I was really focusing on sensory grounding, the focused on sensory connection to sensory systems, sensory inputs, sensory representations. But I think a lot of what I said also applies to sensory connections to the external world. Whether it applies to connections to the external world which aren't via senses is more complex.
So I agree with this categorization of different types of grounding, but I think the argument holds even for the weakest form of grounding, which is just observational, that visual perception, at least in humans, is very high bandwidth, whereas language is very low bandwidth. And so even if you don't have vision, to learn the similar concepts takes a much longer time because you need to get much more descriptive text, which may be impractical. And I think it's the same thing for computers. Of course, computers can digest a lot more text per second than we can, but the language is still a very approximate, discretized representation of reality. And there's a lot of all of animal knowledge and much of human knowledge is never expressed in language. Anything that requires, I don't know, engineering skills to build a box out of wood. This much of the knowledge in this is not present in language. And if all of knowledge was present in language, then we wouldn't need practice to learn a skill. We would just learn it by reading books. And we go. At least the doctors I see hopefully have more experience in this.
Next question. Nick, why don't you stand up and speak loudly?
I'll do my best to speak loudly. So I want to go back to this first question you asked on the role of planning. Is that better? Yeah. So whether planning is indicative of having understanding and whether there's this link. So it looked very plausible to say that the large language models aren't doing planning because they're just putting out a token at a time. But as I understand it, there's quite a lot of cases where the attention head is using something that was a long time ago. So in a sense, and in the very early bits of text, it's got itself into a state that it's ready to use much, much later. And of course, it's only reusing its own outputs. So it's not getting any external things. So there's a sense in which it's planned, right? It's got into a state ready when it's produced lots more tokens. It's going to use that state to produce the next token. So there's a common sense notion of planning, that's planning. Can anyone on the panel give us a notion of planning that's going to rule out autoregressive large language models as doing planning, and will separate them from the kind of thing that Jan's talking about?
No, this really is not planning. So it can appear perhaps as short-term planning, but there's no way that if you don't know in advance what you're going to say in the future, how can you produce a word that is going to be consistent with what you're going to say in the future? This sort of global consistency cannot occur in this case, and that addresses the problem I was mentioning of exponential divergence. You make a small error of tokens that you produce accumulate. Whereas if you have planning, you can ensure global consistency and compatibility with some objective that you have, which does not occur if you do autoregressive production.
Humans are not as good as planning as I think some people think. So when you ask people to categorize a dolphin as a mammal or fish, they mostly get it right. Often they don't, but if they're dragging a mouse, this is Rick Dale and colleagues' work, if they're dragging a mouse, right, and you have, dolphin here, mammal, fish, right, the trajectory is curved. They first start heading to the fish, and then they override it, except in the times they get it wrong. So in many cases, I would say, we often get the answer right, but the planning is it's not like we just plan and then execute, right? We just start doing and correct it as it happens, as it unfolds.
Yeah, I wanted to agree, because I think, so again, if you say that the model knows what it's going to do in the future, which is it's trying to predict the next word, and if it's setting itself up for that by getting all the bits and bobs in place in these earlier layers or at earlier kind of tokens so that it can attend back to that to make a decision later, I think that is a form of planning in that task. So it seems like if the question is, like, we should divorce what is planning, where planning is given you have some future goal, you're kind of planning, putting steps together in a way that helps you achieve that goal. But then that's kind of divorced from what the goal is, or we have an issue with predicting the next word as the goal, and somehow that's the thing that invalidates language models. To me, that's actually a different question maybe than grounding, or maybe it could be made to be the same question as grounding. But those seem like kind of divorceable issues that should be discussed separately.
Hi, I'm Susanna Schellenberg. So I wanted to ask about, so it seems that, large language models are at least indirectly sensory grounded because they operate on the language we use, and, our languages are sensory grounded. And so, to connect it to the example of the congenitally blind person who understands transparency, they understand it because they hear people who are not blind talk about transparent things. And so, in a sense, sort of pure, to use Dave's phrase, pure language, large language models don't exist because they're all indirectly centrally grounded.
Ellie actually made that point in her talk.
Right.
Yes, very briefly, and said someone else will make it more. And I think it was made more by Gary.
Yeah, but I think one thing this brings out is that if the issue is external grounding, interaction with something in the environment, well, large language models actually have a lot of external grounding because, all their words come from a linguistic community and they're sending outputs which are acting on people. That's a lot of external grounding. Is it sensory grounding? Well, it's complicated issues about what counts as a sense. It's not very much like a human sense, but that's itself a delicate question.
But this also applies to communication between humans. We learn a lot of things from other people, and they might have had certain direct sensory grounded experiences, and we learn it indirectly. I don't think that makes that knowledge, it's different, but it's not meaningful because it's now kind of only indirectly grounded.
Can I add one thing to that first, Ned? It is important to clarify though that like the notion that like a large language model like GPT-3 that has no access, no contact with the outside world besides through text. And yes, you can have very meaningful interactions through language. We can learn a lot through language. And the examples from Marina Bedney's work that you gave, Gary, it's amazing how beautifully, similarity judgments and property judgments can align between congenitally blind individuals and sighted individuals. Of course, as people, whether we can see or not, we have a tendency to focus on vision because it's easy to show examples on slides. But as people, we live in the external world. We have other sensory modalities. We know there are things in the world. We have experiences with them. That's very different. We don't get all of our knowledge through text. These systems are really getting their knowledge in a different way.
Sorry, I think the debate isn't, do language models have sensory grounding, right? Obviously they don't. It's, do they need it for meaning, right? So I just wanted to put that out there because I feel like a lot of the answers are like, I don't think it's really being debated. Maybe there's some things about external grounding, but I don't think it's really being debated that language models have that. It's whether they need that for meaning, right?
I think just to respond to an earlier question about different meanings of sensory grounding. So I focused on the kind of direct sensory grounding. I think the causal bit is super interesting. So I would not have expected, like others have said, that adding sensory grounding, these multimodal models, that it wouldn't improve performance. I would have thought that it would. I think adding direct interaction with the world, my bet is that that's what would allow the models to learn with far less data. The reason kids are learning much faster isn't that I don't think it's because of the sensory grounding. I think it's because they're exploring the world and running little experiments.
Not in the first 3 months. Yeah, basically no effect on the
That-
first
so-
3 months except their own news.
But I agree with that. I would argue that 3-month-olds really don't know very much.
They also cry a lot and they get a lot of reactions for the crying, right? So they're not like playing with blocks, but they're crying and they're blinking and they're, turning their head to breast and things. So I mean, they're interacting.
So house cats know more about the world than the biggest GPTs.
Okay, go ahead.
Yeah, hi, Cameron Buckner, philosopher. So the question I was going to raise was actually the point that Lupian just made about, trying to square this apparent tension between the yes camp's claim that sensory grounding should count and Pavlik stated that it doesn't help. Is it because it's not being driven by the kind of world model or active interaction that you would expect? Is that a way to kind of square the two camps? Continue to track you.
But if you want an AI system that can plan actions, it needs to understand the effect of its action on the world. So it needs to be able to establish this by either experimenting in the world itself or by observing other agents that influence the world and inferring their actions. Otherwise, of course, you can't plan. So what happens from purely observational data in the first few months of life for babies, for example, you may learn a lot about the structure of the world, but you won't learn causal model that will allow you to act in the world.
Just want to pick up on something Brendan said about other modalities. I can think of smell where ground truth might be somewhat murky. How would that affect language models to not have that sensory ability of smell? Would that not limit their meaning and understanding?
Has anyone developed a smell language model? Vision language model? Audio language model?
So the only people who have smell language models are wine critics.
In the middle?
Hi, Ida, Microsoft Research. Thank you so much. This has been amazing. I wonder, Jan, I really appreciated your talk. I do think LLMs need a prefrontal cortex, so I'm very much with you. However, I do wonder whether your notion of meaning requires agency. You talk about planning, you talk about interacting with the world. And I wonder to what extent we actually necessarily need agency to understand something or to have meaning. Obviously, the whole Mary issue of Mary knows colors, is a scientist but can't see colors. Does she really know color? It is related to that. But I think it's a little bit more than that. It's not just sensory perception or sentience you're thinking about. You're really thinking about agency with regards to them. I wanted to ask about that.
Yeah, I think there are several levels. So there's one level at which you learn how the world works through pure observation, and there, that doesn't give you agency. And then there is the way you learn about the world by observing other semi-competent agents as acting in the world, you can infer what action they take. And then the next level is you take an action yourself and you observe the result. Right? So those are kind of, it's a hierarchy, and I think we go through this in development because we can hardly act in the world as young babies. LLMs don't have a prefrontal cortex. They don't have motivation, so they don't have a basal ganglia. They can't really plan or predict, so they don't have a prefrontal cortex. Basically, what LLMs do at the moment is that they are approximately decent model of the Broca area, which is a tiny area right here that makes you produce language. And the rest is absolutely model. Now, there is some experiment that was done by some of my colleagues at FAIR in Paris, Charlotte Cocheteau and Jean King and Alex Grandfort, and they had a paper in I believe it was Nature or Science recently, where they tried to explain observations in activity of the brain using fMRI and trying to correlate it with when people kind of listen to stories and try to correlate this with activities you observe in things like large language models. And what they don't find that large language models are a good explanation for what you observe in brain activity. Whereas if you do this for vision, you use a convolutional net or something, and you correlate the activity of the visual cortex, you can explain to some extent the activity you observe in the visual cortex using convolutional nets or other types of neural nets. So there's something structural in the architecture that we're probably not capturing. Their hypothesis is that the brain does much longer term prediction than current LLM that basically do this sort of prediction.
But agents is necessary for me.
No, so I think it's a hierarchy. The first stage, no, you don't need it. I think you can run a lot better well with that acting.
That's our next debate topic.
Hi. Jan, one of your arguments is that current models are doomed is because they kind of accumulate the errors, right? And but this is an assumption if you assume that like predicting a lot of tokens has only one correct answer. But could it be true that there are multiple answers and like the probability is actually not that low for them?
Yeah, so no, I'm not assuming that there is a single correct answer. I'm assuming there is a set, and that set is small within the set of all possible answers, which is obviously true. The assumption I'm making that implicit is that the errors are independent, which of course they're not. So that the probability is multiplied.
Thanks. My name is Emmanuel. I'm a philosopher at Rutgers, and I was wondering if we accept the distinction David drew between the domains on which the models can reason without central grounding and the domains in which it can't. But I wonder what the panel thinks about whether the issue of morality, would that domain fall in one or the other?
Was the question whether moral thought and reasoning would fall into the group of domains one could reason about in principle without sensory grounding?
Yeah.
I'm inclined to think so. But yeah, I don't see an obvious reason why morality has to have a ground in the senses, but other stronger empiricists might disagree.
Mm-hmm.
But morality is an objective that you have to optimize for, that you're not going to get by just predicting tokens, no?
That's what you say.
It is disconcerting to think about reasoning about morality without having any direct access to the outside world and knowing there are things in the outside world besides what you hear from text. So that's an interesting question.
Dave in his talk asked whether sensing can boost thinking. I would want to propose that in some cases it can impair thinking, right? And so, the fact that we feel better about, cute animals, right? Like that's sensing perhaps interfering with our moral reasoning. And to Jan's point about vision being higher bandwidth, it is of course true, but more information, higher bandwidth is not necessarily better. Part of what language does is it categorizes the world in ways that are useful for humans. So one could argue, in principle, right, that a model exposed to only language, right, is getting, in some cases, sort of more streamlined, right, more kind of pure relational data that is more useful, at least for certain types of cognition, reasoning tasks, than the messy world of perception. After all, like part of what makes it hard to educate people to teach, right, is that we are teaching people to abstract away from the perceptual specifics, to transcend the specifics that is perception. And that's a hard process. We're very, in general, by default, I would argue, very concrete perceptual in much of our thinking. And language is kind of an entree into more abstract reasoning. And so it's really interesting to see that these big successes or current successes in AI are coming from the language models. I think many of us in CoxI, depending on where the camp we're coming from, would not have expected that.
There's no universe in which any machine learning person would declare that less data is better.
But I do very much like that point that language really distills and clarifies certain type of knowledge, and I think a real potential path here to understand how these systems know so much and are clearly intelligent in many ways, but also seem so alien and different from us in the way that particularly they acquire their knowledge is it's quite likely that there are multiple paths to genuine knowledge, of course, right? And we as people, when we have world models, when we have multimodal experiences, we have a very different path. It's a much more efficient path. But you can get to some of the same places, not all the same places, and just still that's why I'm in the yes camp, but you can get to some of the same places by analyzing all the text written and posted on the internet, right? And especially for certain types of knowledge where it's highly distilled. So I think that's what's happening. And it's an alien route to get there. Sometimes the knowledge might seem, the reasoning might seem a little alien to us, but that doesn't mean it's not a type of meaning.
It's also worth stressing that the debate title actually was not about knowledge. It was about meaning and understanding, which I take to be a lower bar. You know, so maybe a system could have moral concepts, even scientific concepts, and could mean things and could understand. Now, would a being without senses be a good, say, scientific reasoner in the sense of getting to the scientific truth? Well, no, obviously not. It would need access to the external world for that, but it could nonetheless understand certain concepts at least, and think and have meaning. So I'd really distinguish the question of knowledge and reasoning from the question of meaning and understanding.
Hi, I'm Sam. I'm a student in Ellie's lab. So this question is primarily for those who think that there are facets of meaning that a multimodal model can attain, which a text-only model in principle can't attain. So it goes without saying, obviously, that a multimodal, say a vision plus language model, doesn't have eyeballs. What it has is image data in a certain encoding. So say, for example, it has image data in the form of series of pixel values that are associated with the input images. So in principle, one could replace that quote unquote image data with linguistic data that just describes exactly that image data in more or less fidelity. In the limit, one could linguistically describe the quote unquote image data in perfect fidelity. So you could, for example, take the flattened pixel by pixel image values and just replace that with a long sentence that goes start of image. The first pixel is 276 red, 112 green. Just write out the picture in words. And so in principle, one can have exactly the same information in text-only training data that one can have in multimodal training data. And then in principle, anything that can be learned from the quote unquote multimodal data can be learned from the exactly one-to-one mapped language data. So the question for those who have been claiming that there are things that in principle, notions of meaning that in principle can be acquired from multimodal, that can't be acquired from text-only data. The question is that because of the input being distinctively non-linguistic, or just because of the input being more data and additive data that is not the kind of data that is usually found in books? So are we talking about linguistic versus non-linguistic, or just about what's usually in text versus what's not usually in text?
Both. So it's both a question of volume. So text is produced by humans, and for that reason is in limited supply, even though it's very large. Whereas video data, for example, is essentially unlimited and infinite for practical purpose. So there is a question of volume, certainly. You are in principle right that you can always serialize or tokenize all the information in an image and turn it into a string of bits or a string of symbols. But then there is a question of architecture. So what is the proper architecture to understand the context of those images? Can you understand the content of an image by merely feeding the sequence of RGB values to a transformer, which is the kind of architecture that is used for language? And that works to a certain extent. It's very inefficient, but it works to a certain extent. What people do in those multimodal systems currently is that they so-called tokenize images. So they break up images into little squares of 16 by 16 pixels or something, and then turn each of those into a token that is kind of like a word, but it's represented as a continuous vector of certain dimension. And then you feed that to a transformer. And since the function computed by a transformer is equivariant to permutation, it doesn't care the order in which you feed the tokens, as long as it's always the same order. So there is some truth to what you're making, but it's basically it comes down to the question of efficiency. I mean, there are similar debates that can lose a bit of their meaning if you talk merely in principle. So, for example, in principle, you don't need giant neural nets with 96 layers or whatever it is. You can do everything with just 2 layers. It's just extremely inefficient, and so inefficient as to be completely impractical.
Can I just follow up on that? Because I liked the point Brendan made. Like, I think things like efficiency don't directly weigh in on this question, right? Like, obviously, like, it would be ridiculous to claim there's anything human-like in the way that models are trained. I think that doesn't mean they couldn't have human-like representations as the end state. So if it's a really inefficient route to get there, so be it. I don't think that precludes them from meeting the bar for meaning and understanding, unless there's like a really good case to be made for why the efficient process will lead to a difference in the end state. So I think we need an example, like a compelling story for a difference in process resulting in a measurable difference in end state. If it's just a difference in process and you get the same end state, I don't see why efficiency is a relevant factor.
So Raphael, this will have to be the last question.
Rafael Munier, philosopher at Columbia. So we've been talking a lot about next word prediction, and I think there is room for discussion about the extent to which models trained with next word prediction can plan ahead by pre-computing possible paths to completion, evidence for mechanistic interpretability, for example, that Nick alluded to. But leaving that aside, current language models, the latest ones at least, don't simply get trained with next word prediction. They often get fine-tuned with reinforcement learning from human feedback, right? And that involves getting crowd workers to often rank outputs of the model according to certain normative goals, some of which are epistemic goals that involve truthfulness or honesty. So my question, especially for people on the no side, is whether you think that makes a difference, because arguably this kind of policy that you learn with the real world model there would learn a world involving function, at least much more world involving that than next word prediction.
Yeah, I don't see why it makes a difference to possessing the concepts, but I think it certainly could make a difference to whether they have knowledge, because they're reinforced for saying the truth in some domains. So I draw that distinction again.
So I think I may be wrong about this, but I think the reason why this is so useful, this RLHF reinforcement learning through human feedback, is that most people ask similar questions, and so if you adjust the system to correct the answer for common questions, it will work okay. But as soon as you go outside of the type of questions that have already been asked, then you are out in space. And I think it's kind of hopeless, because the number of possible questions is a very long tail. You're never going to see that long tail during training. There are always going to be a lot of type of questions that people are going to ask for which there is no feedback that is directly helpful. And so I don't think this is going to fix the hallucination issues or confabulation rather that those models have completely. Is going to mitigate it, but not fix it. The only way to fix it, in my opinion, is to redesign those models so that at inference time, they optimize objectives that are clear. That I can't imagine any other way of doing it. But I keep repeating this message.
Okay, so. Okay, there we go. Okay, so there's now going to be a reception in the Silverstein Lounge in the Silver Center. The Silver Center, I think, can probably be best entered at 31 Washington Place. It's right adjacent to the park.
No, Waverly Place.
Oh, sorry, no, Washington Place.
No, the main entrance for,
No, no, I
people
don't-
cannot get in.
Oh, they can't.
I believe that we're gonna have check-in on Waverly Place.
Oh, okay.
32
So,
Waverly
yeah,
Place.
all right. So
NYU people can get in, because who will not need any other registration can get in at Washington Place.
okay, all right. In case that isn't true, there's another door on Washington Place. And let us thank our panelists